Pleasure to introduce Dave. Should need no introduction as the man who coined the term RISC. He can tell us about our compressed extension very quickly.
Okay. This work has primarily been driven by Andrew, a waterman, but he can't give two talks in a row, so I'm doing this. So the compressed instruction set, it was originally inspired for the low end, but from the beginning we talked about at the high end the benefits for reducing the cache footprint. So this was released a month ago, and the whole idea is instead of having just 32-bit RISC instructions is to also have 16-bit RISC instructions. And you have a 5 or 6-bit opcode, and that leaves 10 or 11 bits, so you can have two 5-bit address fields or for registers, or a 5-bit register field and a 5-bit immediate, or we have the 8 most popular ones, so we only use 3 bits. We could have 2 of those in a 5-bit immediate, or 1 of the 3-bit fields and an 8-bit immediate or 11-bit immediates, and that's it. The novel idea, and I think it's elegant, is that instead of having a separate instruction set, it's really just a compressed version of existing instructions. So all the decoder has to do is to take the 16-bit compressed one and translate it into the existing 32-bit address one. This means the compiler doesn't have to be aware of it. It can leave that to the assembler, and the assembly language programmer doesn't have to be aware of it. That'll just happen for it automatically. And the bottom line is with a modest number of instructions, half of the instructions in the program will be 16-bit, and so if half are 16-bit, that turns into a 25% reduction in code size. Kirsta showed this earlier, is that the RISC-V instruction built in has a 16-bit opcode, and the thing to keep in mind, that uses up most of the opcode space. So you can't easily retrofit a 16-bit in because you can't have that many opcode bits, and out of all of the instructions you use, that uses up a lot of opcode space. And then to support it, all you needed to do, as Kirsta said, is not say we're going to have 32-bit aligned instructions. We're just going to have instructions 16-bit aligned. It only costs you 1 bit of address space to support it. So the cost is a lot of opcode space and a little tiny, smaller branching. We are not the first people to do this. ARM did this with the thumb instruction, which was a brand new instruction set when they did it, and you had to change modes to use 16-bit instructions. All the instructions were 16-bit. That didn't work very well, so a couple years later they did thumb 2. MIPS did something along the same lines. They had a mix of 16 and 32-bit instructions. They're actually a different instruction set, and they could go back via a mode change. So that all happened pretty much in the 80s, and some of them in the early 90s. So what did we do, or what we, the faculty, is Andrew implemented everybody has an opinion about instruction sets, and almost the same number of people has an opinion about how to make them smaller. So lots of proposals were put forward. Andrew implemented them. We ran them on the spec integer code bases and some other code bases, and so it wasn't philosophical, it was quantitative. If it didn't work very well, we didn't include it. And all of us had suggestions that didn't work very well. So how about 3 popular registers in one instruction? That didn't work very well. How about this, Baroque, ARM v7, ARM v8 ideas, not just an immediate field, but you could repeat patterns or table lookups. That didn't work very well. It worked a little bit, but it used up a tremendous amount of opcode space, like the short loads and stores or floating point loads and stores. The floating point loads and stores, not that many, there's lots of programs that can't use them at all, especially since it's optional, but it wasn't that big a benefit even for the floating point programs relative to their cost and opcode space. So the bottom line is Amdahl's law, right? There's a few instructions get most of the benefit, and as or the law of diminishing returns, you get to the end, there's not much left to gain. So the first 10 instructions save 14% code instructions, the next 10 are 6, next 10 are 5, and after that we have an elaborate 24 more instructions, and it only got 1%. And in the thing that we released, we asked you to give us feedback on what we call the extended RBC versus the so-called standard ones on what we should do. And then we have results that are 3 days old at the end about something in produce code. So this is one of the formats. These 4 instructions all by themselves are 7.5% code instruction. So move is one of the most popular things you can do. You can see we have the 2 source fields. It expands into this add instruction that uses the 0 register to add 0 to it. Add word and subtract. A popular thing to do is do loads and stores off the stack pointer, so we have that encoded instructions depending on the width of the data being 32-bit, 64-bit, 128-bit words. And it scales the immediate field by the size of the data you're transferring in bytes. So that gets us up to, those 3 instructions gets up to 11, and the store gets us up to almost 14% of the symmetric instructions there. Then we have regular old loads and stores we specify one of the popular registers for the source and destination. Those 6 get us up to 16.6%. And then finally, there's loading some constants. Loading an regular immediate and loading the load upper left. And the last few of these, of the first 20 instructions is adding immediates, adding immediate words. So that's 20%, so that's 40% of the instructions out there are covered by these instructions. The next 10 get us another 5 instructions, so conditional branches, jump and links, a single shift, and some fancy add with the stack pointers to get that are scaled. And finally, we need to have a debugging instructions for 16-bit code, so that's included. So that's the 30 instructions that gets us 25% savings. Here's the one that we're asking your opinion about, and I grouped them into subjects, and you can see that they're fractions of percentage for these instructions that put in there, and let us know what you think about including them or not. The argument for including them isn't, we don't have the data to support it, but maybe new compilers, maybe new programming languages, maybe assembly language programmers would use them more than the GCC compiler does. So we look forward to your opinion. So what's the bottom line? So what's shown here is code size. We take the spec in 2006, you compile it, use the compressing assembler, and see what happens. And is there a pointer? This might be a pointer. Well, it's a small pointer. Okay, so it's relative to the compressed code. And the first set of ones are the, well, that was it. The first set of ones are the 32-bit instructions on your left. The thing that was surprising to me was how bad the MIPS code was. And I think we think it's because of the load branch delay slot, that thing that doesn't make sense anymore. So it's, the regular RV32 is 34% bigger than the compressed. Okay, great. Okay, so that's, that's the 25, this is 25% smaller than that. x86 is bigger. This is the regular ARM v7. This is thumb, which is smaller. The MIPS and the MIPS 16. Now, when we go over to the 64-bit address space, because they didn't leave space for it in the opcode, they couldn't retrofit the 16-bit things in, so none of the 64-bit address space, except for RISC-V, has the 16-bit encoding, so it's a lot smaller here. And so we're smaller than everything except for Thumb 2, which is one of our main competitors. I think, and then I calculated the averages there, so 35% bigger than RISC-V or 28% for that set. So a thing that we spent a lot of time talking about was load and store multiple. Well, kind of a RISC idea is you don't want load and store multiple, but it's useful on saving and restoring instructions. That's one place where you're going to save a bunch of way, and maybe whether or not it's faster, it can save code. So this idea, and I don't know if this was suggested from outside or where the initial idea came from, but there's another idea you could do is instead of having a bunch of loads or a bunch of stores to save or restore registers, what we could do is do a procedure call and have the procedure call save or store registers away. And so you can do that at the cost of one 32-bit jump and link and one 32-bit jump in the code space, and then you jump to the place where you're going to save and store away. And if you have a sequence of register saves, 8 of them in a row, you can just jump in the middle to get the last 4 of them. And so that's how it's done. So that shrinks code size another 5%. So that compiler trick all by itself is more than dozens of instructions that we propose. When we renormalize to that, you can see, well, RISC-V just happens to be the smallest one by a significant margin. And all the other numbers get a lot bigger. So it's now, oh yeah, the average is 34% smaller, 30 or 40% smaller than the other ones. Okay, so we are ready. Yeah, questions? Lots of questions. Like I said, I used to fool around with instruction set encoding, but all of us have opinions on how to do that. Yeah, go ahead.
Is that a fair comparison? That's
You said,
like,
identify yourself and then.
oh, hi, Rob Taylor, Nerebus. Is that a fair comparison? That's like, because the other one's getting the same compiler trick.
This is just using us. I don't think it makes sense for ARM because it has to load multiple, store multiple instructions.
Yeah.
If the other ones, do the other ones implement this? No, we didn't modify all the GCC compilers.
Yeah. Cool.
I think MIP16E might also have that too. One thing I just mentioned, Dave, these numbers with the 32-bit jump and link for the save and restore, we actually have a 16-bit version that's actually bigger saving than this. I think this doesn't include that either.
That doesn't
so
include that,
another
yeah.
4 bytes per instruction smaller when we get around to doing that as well. 4 bytes per function.
Hi, Dave.
Yeah, where are you? Okay, yeah. Hi, George.
Yeah, really impressive and very useful as well. I'm George from Intel. And do you have overall evaluation after this compression regarding the power consumption? And
Power consumption?
Yeah.
Yeah, we don't have anything like that yet. I think several of the core comparisons include a power consumption comparison, not including the compressed instructions. I would think this will, as the most experienced person here, based on my experience, that's my qualifications. I think it'll improve power even more because of the if it reduces cache misses, it's going to get an even greater benefit from that. And I don't think, because this is a really simple trick, right? We're translating from 16-bit to 32-bit. I don't think the decoder is going to be that much more complicated. So I think the extra cost, the bigger decoder, will be a small gain compared to the power savings. And already I think right now compared to the ARM cores, power is significantly smaller for RISC-V than that. So I think this will further separate the gap. But that's an opinion. I don't think we have any data on that.
Just to follow on, everything except this last trick should be strictly a performance and power gain from using compressed. There's never any, but this last thing of using the procedure code to do save and restore, we're going to make this, it's actually just bound to dash OS and GCC. So if you do compile for size, dash OS, they'll do this trick and save you that extra 4%, but that will come at some performance penalty because you do those extra jumps to get to that routine and back again, which may add a little bit to the power, but whether that's probably more or less depending on the core, depending on the iCache savings you get from doing the same trick. So we don't know, but if you don't use this trick, if you just compile -02 and just dash MRVC, you'll strictly get a performance and power improvement from using compressed.
Thank you. Yeah, I think we're safe. And reason is a lot of I/O power, which consume a lot as cache. So we were waiting for data. Thank you.
Okay. Are there other questions on this side, I think? Oops, okay.
Hi, Guy Lemieux. Did you look at the impact on the constant pool and see if some of the load upper immediates and things like that are being reduced and spilling extra data into the constant memory area? And then you're only looking at the aggregate.
I don't do two-part questions very well.
Sure.
I'm not sure I understand the question. You mean how much bigger was the constant area because of the, so.
You have smaller immediates in the compressed format, don't you?
Yeah, but the reason why it's always strictly a gain is that it doesn't fit the 16-bit.
Right. Well, I can do that one. That one I can answer. Because it has both 16 and 32-bit instructions, right? So if it doesn't fit, you use the 32-bit instruction. Otherwise, if it fits, you use the 16-bit. So Yeah, it can only help.
Okay, can I do part two?
Yeah.
Do a quick follow-up.
Oh, okay. All right. Maybe
Sorry,
not.
I just want to add as well that I forgot what I was going to say.
We have this on videotape, right? Krista's getting more senior. Okay.
This is measuring aggregate code size, but there's also, you're saying some of your workloads were for instruction cache sensitive applications where maybe loop kernels have to fit within a cache line and things like this. Did you look down at the micro level of the impact on the compression? So some of those instructions that you didn't get benefit for might be good enough to keep things in a cache line, for example.
Yeah, but they have to, yeah, but, you know, it's worked pretty well to use static code size for that. Andrew in his master's thesis documented the benefit on instruction cache hit rates and bits transferred in his master's thesis. But I think it's pretty highly correlated. It would be surprising if there was a dynamic instruction that didn't occur very much statically that would make a big hit on cache size. That'd be a kind of surprising result.
James Ho, CMU. On your first slide, I think you said the compiler and assembly programmers don't need to understand this change.
The assembly, yes.
Can you explain what that means?
Yeah, so we're doing, because of, I think, this elegant idea of the 16-bit instructions are translated into existing 32-bit instructions. If the compiler is producing assembly language, it doesn't know about it. If the assembly language programmer is writing assembly language, it doesn't have to remember, you know, like an ARM, you know, is it a, you know, can I represent this constant in this 12-bit field? You know, the assembler just handles all that. So it will automatically pick between the 32-bit version or the 16-bit version. You don't have to worry your pretty little head about it. The assembler does the compression, basically. You could, yeah, you could. If you wanted to, yeah, if you wanted to make the compiler smarter and the compiler might get some more benefits, the compiler certainly can generate it, but there was some questions on the discussion group about, do we have to write both, you know, put the C in front of the moves and stuff? You don't have to do that. You can do a second pass. Okay, Kirsta remembered now.
That's what I was going to say earlier on. So exactly that. So the point is we did it in a way that the compiler and the assembler can be oblivious to that change. And actually, at link time, there's a link relaxation that happens. So one thing that happens is you shrink instructions. What you might find is a branch now that used to not be able to be within range is now within range. So the linker, Andrew did all this work where the linker does relaxation, actually crushes your code down, and as the branches become in range, it crushes those down again, which may in turn cause another branch to now become in range. So it kind of does all that fine trickery, mostly in the linker. That's right. So we've done it in a way to simplify bringing everything up. The toolchain can be oblivious all the way down through the assembler to whether these instructions exist and how that lets us do this research very quickly. And actually works okay in practice. Later on, the compiler could be made aware of this. Andrew did do something to bias its heuristics to favor the 8 most common registers. In practice, it did mostly that anyway. So yes, theoretically, you could do a bit better by telling the compiler this exists and to schedule and optimize code for it. That's what I forgot to say earlier. It's just lack of sleep, not more years, I think.
Yeah, that's what they all say. Yeah.
Rishi or Nikhil from Blue Spec. Actually, my question is just following on the same topic, which is I think I like the idea. It has a positive effect that you just said that the upper end tool chain doesn't need to know about it. But isn't the downside of that the compiler writer chooses a different instruction selection algorithm and suddenly your code blows up? Because
it's just not possible. I've been doing this too long. It's like you said, the instructions that everybody uses are really simple, right? And they compress. You know, it's there's popular registers, popular instructions, and fairly straightforward things will result in half of your program using 16-bit formats. But basically, we got to the 25% number. There's a bunch of ways to get to a 25% reduction. It's really hard to do a lot better than that. Intel built a computer that had bit variable length instructions, right? You could do something exotic to try and get more than this 25% code reduction. But I don't think something's going to happen that will blow it up. It's just hard to do.
Yeah. I mean, one experiment would be to run it through LLVM as well and see
Yes.
what happens there.
we would love to, that would be a great, that's, yeah. Part of the reason that we're doing this open source is we would love for more people to work on projects. There's lots of interesting projects to work on. It'd be great if other people would help us.
Hi, I'm Yunsuk Lee from Berkeley.
I'm sure this is a question.
No, it's a comment. You know, if you're interested in this discussion, you know, we made a mailing list recently called isa-dev at list.risc5.org. So, you know, if you want to be kind of into the discussion about ISAs, you know, then please sign up. That's all I wanted to say.
I was hoping Yunsuk was going to ask me a question about RISC-V. Well, it didn't work out.
So is the compressed...
This is Peter Xu from
Peter
Oracle.
Xu from Oracle Labs, I'm sorry. Is the compressed instruction set just part of the instruction set? Or
It's one of the optional extensions.
So do you have to be in a certain mode to have it
No.
enabled?
Well, no, we don't. It's when you know, we don't have modes, right? It's you're choosing which extensions are being implemented, right? And you can do you have floating point or not, right? That's a choice you can make when you build a RISC-V. Do you have compressed instructions or not? That's, you know, does that make sense?
Maybe get a little more. If you build a machine that supports the C extension, it will run code that didn't use the C extension perfectly well.
Is that what you're
It's
worried about,
strictly
binary compatibility?
yeah. So your binary compatible machines that don't have, with binaries that don't use C. If you build a binary for, well, it's like if you just get traps, right? You just trap on every 16-bit as an illegal instruction. If you try and run binaries with instructions that aren't implemented, you'll get traps.
We wouldn't recommend it. That's why G is defined, not including the compressed instructions.
So the 32-bit instructions in the binaries that have the 16-bit instructions are on 16-bit. It's okay to be on 16-bit boundaries.
Correct.
Right? And so in general, is the ISA defined so that 32-bit instructions are on 16-bit boundary, okay to be on 16-bit boundaries?
If you don't implement the C or any other variable length instructions, if you only have 32-bit instructions supported, then you only have to worry about 32-bit naturally aligned instructions. They won't be on 16-bit boundaries. The base instruction set, though, does have jumps and branches targeting 16-bit boundaries as part of the ISA. But your implementation only has to worry about 32-bit naturally aligned instructions unless it implements the 16-bit or greater than 32-bit instruction set extensions. One thing, if you wanted to, you could support the behavior of if you implemented C, but wanted to trap on C, that would be a hardware thing. You could have a mode in your machine mode that would set a bit saying, I've implemented C, but I want to trap if this binary uses C. You could do that as an implementation-dependent thing if you wanted to, you know, emulate not having C on a machine that has C.
Right, but I mean, it seems to me that, like, for high-performance implementation, you're going to want the compressed thing because the iCache performance is significant.
Yep.
Yeah,
So,
I agree. You'd want floating point too, right? So,
yeah.
Yeah. So, yeah, I think C will be a popular extension.
Frank, LG. I'm wondering, David, if this wouldn't be a better idea to make this C mandatory, because it's really it's a disadvantage. And how big did you check how big the overhead is to do it in the decoder?
I think this would be
Philosophical.
let me give the philosophical. I think this would be the type of thing why we want to have a RISC-V foundation, right? Okay. I'm sure Christian's got an opinion on it, but you know, for issues like this, how are we going to resolve this? You know, Berkeley's going to seed this, but how is this going to grow in the future? I think a RISC-V foundation is exactly the type of things. And the other things can change over time. What's the right answer? The answer could change over time, and how are we going to do that without following the terrible footsteps of all other instruction set architectures? I've spent 3 months of my life trying to understand ARM v8. I just found out there's an ARM v8.1, and they're going to support both ARM v8 and ARM v8.1, and it's only like a year old, right? So it's incredibly big, and it's going to grow, right? And so how do we avoid that? And so I think the RISC-V Foundation has got that chance. But to your question,
So no. So the reason being, the rationale is, I think it would be appropriate to say, for example, like shrink wrap software ABI should include C. That might be a point we get to at some point in the future, right? So the ABI for some, say Linux ABI may involve always assume that C is present because everybody running, big desktop or server machines are going to want to have C in there. However, it's very important that the base I stays as it is and is available as a base to build on, where, for example, I'm building an accelerator, the compress doesn't help me, right? Or I have tiny code loops, it doesn't really matter. I'm not going to worry about 16-bit alignment in that instruction fetch unit if I don't need it at that I. But that I is enough to run, all the code base I need, like C compilers and everything else, be ready and working. Also, when I teach a class, I like to teach, this is all you need to know to build a working computer that can run any code. And here's the compiler, and it generates code for I, and it all works. So there's multiple reasons why you don't want to make C mandatory in the architecture. However, a given ABI may be built around a given set of extensions. So, so GC and maybe V, vectors we'll talk about later, that might be all assumed to be present in a sort of shrink wrap software ABI standard.
So the difference between the ABI and the required for all implementations, okay.
I just wanted to make a mention to that. The hard part of the C
This
extension is not the...
Identify yourself.
My name is Chris. I'm a student here at UC Berkeley. The hard part is not the decoder. That's, as we mentioned, is trivial. The hard part is the fetch unit. So if you're doing superscalar fetch, you're fetching across a page boundary, suddenly you're bringing in virtual memory. That's stuff that we don't want to mandate every single, student, hobbyist, company, whatever. That's a lot of stuff for them to have to deal with.
All right, well, I think, why don't we do one more question and then we'll go to break.
So Dave, why did you leave Spark out? This is Venu.
What?
Why did you leave Spark out in that table?
Spark? Oh. You have to ask Andrew that question. I would think Spark would be like MIPS and Spark, but go ahead.
So, just so that I get this right. So
Name?
Oh, I'm Trivikram from Google. So, looks like you're kind of standardizing a compression based on results that you've gotten out of spec in 2006. Is that kind of the gist of it?
We looked at a couple of other code bases, and it worked a little better. But that's, yeah, right. We've been quantitatively driven. We'd be happy to get other code bases to look at. We would, if there's other code bases written in C, we'd love to look at those as well. But it's been a small number of code bases we've looked at. The other one was the Linux kernel.
So my question really was around, if there isn't a representative benchmark at all, does it make sense to even standardize compression?
Yeah. No, I think, my question is, will it change that much between code bases? The relative value of these instructions. What we saw when we looked at other code bases is they got, the amount of compression varies, but which instructions are the most important don't change. So, basically, you need to have, move is going to be your most popular instruction. And that's not going to vary based on the code base.
Sure. So it looks like you're going a little bit beyond move, right? So I'm kind of citing Occam's razor here. That the burden of proof is on you to kind of prove that a one-size-fits-all standardization of compression would work.
Okay, we'd love to have more code bases to see if it changes.
Actually, the onus is on all of you to give us counterexamples. Right?
Yeah. If you can find code bases, it doesn't work. Okay, I think so why don't
we should take the break because the coffee will get cold otherwise, and we'll start at
11:15.
Let's actually start at 11:15.